everyone. Today we are going to see about the basics of signal and what is a basic definition of signal, how the signal is categorized, what are the different signals that are used for practical applications. So first let us go with the definition of signal. So a signal is defined as a physical quantity that varies with time, space or any other independent variable. This is the basic definition. If we have to say roughly, a signal is nothing but an informative carrier, so which holds some information to convey from one to other is defined as signal. Let me give an example as a signal which is varying with respect to time in terms of its amplitude. So that is a simple example. So when time is in 1 second, its amplitude is certain value. When time is in 2 seconds, its amplitude is 2 volts. When time is 10 seconds, its amplitude is 100 volts, like that. So signal is changing with respect to time, that is independent variable. This is also one type of definition we can frame. Now we'll see the main categories of signal. So a signal is basically defined of three types: continuous, discrete, digital. So what is the continuous signal? We'll see. Continuous means we can say the signal also as analog signal. So continuous in time as well as in amplitude. This is the definition. Discrete means discrete in time, continuous amplitude. This discrete time indicates what? We'll see in this. Digital signal means what? Discrete in time, discrete amplitude. So these are the three basic categories. We'll see one by one in detail. Continuous signal or analog signal. So first, continuous time, continuous amplitude means what? When we take certain time, for suppose from 0 seconds to 1 second, what is the internal time? Each and every fraction of time from 0, 0.1 second, 0.2, 0.3 up to so on 1 second. In the similar manner from 0 to 1 volt. I am taking examples. That's why I am defining from 0 to 1. So 0 volt, 0.5 volt, 0.6 volt, 0.7 volt, 0.8 up to so on 1. So fractional values are also present. For every time sample it is having its amplitude. That is continuous signal. Discrete means what? Discrete time means I'll take only a selected range of time, that is perfect integer we can say. 0 at the time value, 1 second value, 2 second, like that I'll take here. Continuous amplitude means as we discussed in the first case, so it contains fractional amplitude. In the similar manner, if we go for digital signal, discrete time, discrete amplitude means perfect integer values of time with respect to its amplitude. We'll see how the representation is done. So here we can see continuous time, continuous amplitude, first category. This is the representation. For every value of time, for every amplitude is defined here. For what time, what is its amplitude? Here time, what is its amplitude? So it is also changing from one to other continuously. So its shape is also changing. We can observe here. This is continuous time. It contains fractional values also. Here continuous time, discrete amplitude, we'll see. Time is continuous, means time is differable all cases. So at this time sample its amplitude is +1. At this time sample its amplitude is -1. At this time sample also it's -1. Here we can see amplitude is stick to +1 volt or -1 volt. So means it is also a perfect integer, it is also a perfect, does not contain any fractional value. That is the main intention I want to convey. So here continuous time means it contains fractional values of time also. Here discrete means it contains only integer values of amplitude. Here we can see in discrete signal category, discrete time, continuous amplitude, the reverse case of this. So discrete time means what? Selected time samples at 0, 1 second, 2 second. Here in this portion I can say it is simply 0. I did not consider this time. Here I am considering, whereas here I have considered all the time ranges, but here not. You can observe the difference between those two in the pictorial form. Now, here I can say amplitude is continuous. Here I did not define, means it is saying that here continuous means I am taking amplitude as fractional part also. Here it may be 0.5 volt, it may be 0.6 volt, it may be 0.2 volt. So this is the case of discrete time, continuous amplitude. These two combo I can say as discrete signal. Now what about the digital signal representation? What is the difference between discrete signal and digital? We'll see now. Here I can say this is discrete signal because here time is discrete. By seeing itself, I can say I have selected only particular values of time, not every case. So at this time, this time 1770, what is its amplitude? 0. At next time sample 1771, I can say what is its amplitude? 100. Next here, it is certain value. Next here, it is in between those two values. This third sample is in between these two, means it is a fractional value. So I can say it is a discrete time continuous amplitude, so that it is discrete signal. But whereas here you can see, here I can say discrete time samples taken as well as discrete amplitudes also taken. Here see, at time 0th sample it is having, let me take 1. At time equals to 1, it is having amplitude 2. At time equals to 2, 1. At time equals to 3, 3. So like that, it is for perfect values of time, perfect values of amplitudes are considered. So discrete time plus discrete amplitude equals digital signal. This is about digital signal. Next, we'll see the basic differences between a continuous signal and discrete signal. As we discuss the categories of signal, we may expect this for a 2 more question. So continuous means it is defined in all cases. So if I take a certain limit, I can define all the values here. But here I can't because I have restricted my time or amplitude to a particular integers 1, 2. In between 1.1, 1.2 I am not considering. That's why for a certain values I am considering discrete. Here continuous means, as we discussed, it contains fractional parts. So if it has to jump from 0 to 1. Meanwhile, 9 steps are there. 0, 0.1, 0.2, 0.3, like that, 0.9, 1. But here it can directly jump from 0 to 1. So here the examples have given, that is 50.5, some fractional values I have considered, whereas not in case of discrete. Here you can see 30, 35 particular integers. So number of students opting some course are 30, 35, 40, 45. Like that we can see the differentiation between these two. Next, we'll see the different types of signal, basic signals. So first one is sinusoidal, as we know. So 2 types of basic signals are there, that is sine and cos. So cos, this purple line I can say it is cos signal because cos 0 is 1, as we know. Next, this blue line indicates a sine value as sine 0 is 0. So these are the 2 signals which can carry information. Next category is exponential signal. So there are 3 mathematical representation. This is 1 in terms of its amplitude. This is with respect to amplitude and phase form. This is in terms of trigonometric representation. So here we can see the exponential decay and exponential rise plots. With respect to only positive half we have taken. In the down we can see it contains both positive and negative halves. So this is also a type of signal which we can use, so that A may be any value, N may be any value. It contains some fractional parts, I can say directly. So this is exponential signal. Next category is impulse signal. This is very, very important. Impulse is also called as Dirac delta. So it is denoted with del of t. The signal is simple. It is defined at only one time sample, that is t equals to 0. In remaining cases, its value is simply 0. At time t equals to 0, its amplitude is noted. In remaining cases, when t greater than 0 or t less than 0, its amplitude is simply 0. So here we can see the mathematical notation. Del of t equals to 0 when t is not equals to 0. Means when t is equals to 0, then only its condition is applicable. So this is a theoretical assumption. At t equals to 0 time sample only, its amplitude is different. If it is unit impulse, unit means as we know 1, so its amplitude is 1. Directly we can say. If it is not unit impulse, if it is impulse, its value may be 5, 10, 100, 200, our wish. So this is a theoretical assumption of signal. If we come to practical case, this rectangular pulses we are seeing, no? So the duration between these two is denoted with epsilon. When epsilon tends to 0, when it tries to reach to 0, this rectangle will raise and will try to reach value as 1 if we consider unit impulse. So this is the practical notation of unit impulse. So then we'll see how the continuous and discrete representation is there. So here you can see when time is in 0th range, its amplitude is trying to reach to 1. That short period is there, no? So if we stretch that short duration of triangle form, we'll get amplitude as 1. This is continuous. It won't suddenly jump to 1. It will tries to reach to 1. That is continuous unit impulse. Unit we are specifying, no? That's why 1 is kept. If it is discrete signals, means I'm considering time as discrete values, then as I specified unit impulse, so at 0th time sample, its amplitude is 1. We can say this as digital signal also, because 0 is a perfect number, amplitude 1 is also a perfect number. So at time 0th sample, its amplitude is 1. This is discrete representation. Then we'll see the next signal, that is step function or signal. So step is defined for only positive integer values of time. It is not defined for negative values of time. So when t is less than 0, I can simply say the signal won't exist. That's why amplitude is 0, we can see. When t is greater than or equals to 0, means from here it is starting and it is reaching, its amplitude is 1. Its value will continuous. But here in this representation of figure, I have considered from 0 to a. That range, in that range only my amplitude has to be 1. Then also it is defined as 1. Step signal with amplitude 1. So this is about step function. So step means it won't contain any negative value. It contains only positive integers of time. If it is unit step, its amplitude is 1. That's it. Next, if we go for next signal, that is signum function. So signum, by seeing this is the notation of that signal. So by seeing this, I can say it contains 3 conditions of time. Time here I am defining in terms of x. We can define by our own choice. So here time equals to 0. Then amplitude by seeing itself is 0. When time is reaching its positive values, then here amplitude is 1. When time is reaching its negative value, its amplitude is minus 1. We can say by seeing this. So mathematically we can write as signum of x. It is noted with SDN of t or x. So impulse is noted with del of t, as we can see here. Impulse is noted with del of t, whereas step is noted with u of t. So SDN of t, which is called as signum function, so its value, its amplitude is minus 1 when time is negative value. Its value is 0 when t equals to 0. Its value is 1 when time is greater than 1. So this is the signum function. Next, what are the properties of impulse function? What is the interrelation between impulse, step, signum? These all things are very important for external exam, and we'll see in that next video. Thank you.